All right, so in calculus, you've probably gotten really good at using the first derivative to figure out a graph's slope. Is it going up? Is it going down? But that's really just one piece of the puzzle. What about the actual shape of the graph? The way it bends, its character? Today, we're going to dig a level deeper and figure out exactly what's going on there.
So that brings us to the big question, right? We can find the tangent line, we know the rate of change at any given moment, but how do we describe whether the graph is curving upwards, kind of like a smile, or curving downwards, more like a frown? What tool do we have that actually tells us that?
And there's our answer. It's the second derivative. You see, if the first derivative is all about the rate of change, then the second derivative is about the rate of change of the rate of change. It sounds a little meta, I know, but it's the key that unlocks the whole geometry of the function. It tells us about the curvature.
Now, this idea of bending has a formal name in calculus. It's called concavity. And really, any curve can be described as being either concave up or concave down. So let's break down what those two terms actually mean. Here's a super simple way to think about it. When the second derivative is positive, we say the graph is concave up. The easiest way to remember this? It's shaped like a cup or a bowl. It could hold water. And if you were to draw tangent lines on this part of the curve, they would all sit underneath the graph. Now, on the flip side, when the second derivative is negative, the graph is concave down. It's shaped like a frown. It would spill water. And here, the tangent lines would all sit above the curve.
So what do you call the exact spot where a graph switches from, say, holding water to spilling it? That special point of transition is called an inflection point. It's the pivot. And mathematically, we find these spots wherever the second derivative is either zero or maybe even undefined. That's our clue that a change in concavity might be happening. Okay, enough with the theory. Let's be real. The best way to get this stuff is to actually see it in action. So let's roll up our sleeves and do a complete analysis of the function f of x equals x times e to the x. We're going to find everything, where it's concave up, where it's concave down, and if it has any of those inflection points.
Okay, first things first, we need to find the second derivative. So we start by using the product rule on our original function to get f prime of x. Then we do it again. We apply the product rule a second time to that first derivative, and that gets us to our goal, f double prime of x, which cleans up really nicely to just e to the x times the quantity 2 plus x. Now hold on, because here's the crucial insight that makes this whole problem way easier. When we look at our second derivative, that e to the x term is always positive. It doesn't matter what x is, e to the x can never be 0 or negative. So what does that mean? It means the sign, positive or negative, of our entire second derivative depends only on the sign of that much simpler part, the 2 plus x term. And that just simplifies things a ton.
Okay, so knowing that, finding our potential inflection point is a piece of cake. We just set the second derivative equal to 0. And since we know e to the x can never be 0, the only way for the whole thing to be 0 is if 2 plus x equals 0. And that, of course, gives us x equals negative 2. This is our critical point. Now, all we have to do is set up a number line and test the intervals on either side of negative 2 to see what the concavity is doing. And here's what we find when we do that. Let's look at the interval to the left of negative 2. We can pick any test value, let's say negative 3. We plug that into our second derivative. Well, 2 plus negative 3 is negative 1. So f double prime is negative, which means the graph is concave down there. Now for the other side, let's pick, say, negative 1. Plug that in. 2 plus negative 1 is positive 1. So f double prime is positive, and the graph is concave up. And there you have it. Because we see that clear switch at x equals negative 2 from concave down to concave up, we can officially say we found an inflection point. Now, to get the full coordinates, remember to plug x equals negative 2 back into the original function to get the y value. And that gives us our final answer. The inflection point is located at the coordinates negative 2, e to the negative 2. So that's great for a function with an e in it, right? But the real question is, does this method work for, well, everything else? Let's level up and put this process to the test on a couple of different types of functions. You'll see just how universal this technique really is. First up, let's take a look at a good old polynomial, x to the fourth minus 4x cubed. These are usually pretty straightforward to differentiate, so this should be a nice, quick application of our method. So we run through the same steps. We differentiate once, then differentiate again, and we get a second derivative of 12x squared minus 24x. When we factor that and set it to 0, boom, we get two potential inflection points this time, x equals 0 and x equals 2. And a quick check of the intervals confirms a concavity changes at both spots. See? Same process, clear result.
Okay, for our last one, let's tackle something that can sometimes feel a bit tricky, a trig function. We'll look at sine of x plus cosine of x, and just to keep things contained, we'll only look at it on the interval from 0 to 2 pi. But don't worry, the process doesn't change one bit.
So we follow our method. The first derivative is cosine minus sine. The second derivative is negative sine minus cosine. Now to find where that equals 0, we're basically looking for where sine of x equals negative cosine of x. Or in other words, where the tangent of x equals negative 1. On our interval, that happens at exactly 2 places, 3 pi over 4 and 7 pi over 4. Once again, these are our inflection points. The method holds up perfectly.
Okay, so let's boil this all down. What are the key takeaways? It's simple. The second derivative, f double prime, tells you how a graph bends. If it's positive, it's concave up, like a bowl that holds water. If it's negative, it's concave down, like a frown that spills water. The inflection points are just the places where that change happens, and you find them by setting f double prime to 0. And the best part? The process is always the same. Find f double prime, set it to 0, and test your intervals. That's it.
So there you have it. You now have the power to look at a function and see not just its slope, but its actual shape, its curvature. You can pinpoint the exact moments where its behavior changes. That's a huge leap in really understanding the story a function is trying to tell. So the real question is, now that you've unlocked this secret, what other hidden truths about the world around us is calculus going to help you uncover next?